Welcome PCS members and our friends to our Tuesday's PCS IBS seminar. It is a great pleasure to have with us today Professor Nicole Halpern, and I would like to invite our scientific host Dario to introduce our speaker. Please, Dario.
Okay, thank you, Dylan. So it's a great pleasure to have today Nicole for our talk here in IBS. So let me introduce our speaker. So Nicole got her PhD in the June of 2018 in Caltech in California. Her advisor at the time was Professor John Preskill. And her thesis was about, let's say, a plethora of topics, quantum information, thermodynamics, their intersection and applications. After that, she moved, she was, where, let me see. She was a postdoctor in Harvard-Smithsonian Institute for Theoretical, Atomic, Molecular, and Optical Physics. And after that, she became a faculty in Institute for Physical Science and Technology. And nowadays, she's mostly based in University of Maryland and in the National Institute of Standards and Technology. Her research interests are rather broad and cover, let's say, quantum many-body physics, quantum thermodynamics, and intersections between the two. And based on this, let's say, two topics, her talk today is exactly, let's say, at the intersection of the two topics, and it is called the MBL-mobile, Many-body-localized engine. So please, Nicole, you can start.
Thanks very much. Thanks for the kind introduction and for the invitation to be with you. Good morning over there. I'm in California at the moment, so it's evening here, but it's good that we can connect. So this talk is about garbage, or specifically a random disorder potential. So some external potential for some quantum many-body system that looks like it's garbage. It's a dirty sample. For instance, we could have an array of ultra-cold atoms, in which case this random disorder potential could be created by an optical lattice. If you have this random garbage together with interactions between the particles, then you can realize an interesting phase of quantum many-body systems, namely many-body localization, which has a horrible number of syllables, so I'll sometimes abbreviate it as MBL. So MBL has this property. Suppose that you measure the particles' positions, then wait a long time. The particles will hang around more or less in those positions for a while. This behavior contrasts with the behavior of our favorite equilibrating system, a classical ideal gas. Suppose that you measure the positions of the particles in a classical ideal gas. Suppose that you find that they're all clumped together in one corner of the box. Very soon, they will spread all across the box. They will not hang around in those positions for long times. In this way, and in another way I'll discuss, many-body localization behaves athermally or out of thermal equilibrium. If you say athermal to a quantum thermodynamicist, that person might say, I might be able to use this system as a resource in a thermodynamic task. Here's a simple example as to why. Suppose that we are in a temperature T sub H environment, so we have a temperature T sub H heat bath, and suddenly we're given a much colder system. We can let heat flow from one to the other, and from the heat flow, we can extract work. Work is valuable. For instance, we can use it to power our cars. So it makes sense to think of this other system that is not at thermal equilibrium relative to the ambient temperature as a resource. So can we use the athermality of many-body localization in thermodynamic tasks? Well, of course, the answer is yes. Otherwise, I would not be giving this talk. And collaborators and I answered yes in this paper. So I worked with Christopher White, Sarang Gopalakrishnan, and Gil Raphael. We illustrated that many-body localization can be useful in a thermodynamic task with what we like to call the MBL-mobile. This is a quantum many-body engine, a chunk of quantum matter that can be ratcheted between the many-body localized phase and another phase that I'll discuss. Here's where I'd like to go in the rest of this talk. First, I'll introduce the setup in more detail. Then I'll talk about a key property of many-body localization, namely energy level statistics, a property of a class of Hamiltonians, namely the many-body localized Hamiltonians. Then I'll introduce the engine cycle and show how we can scale this engine up toward the thermodynamic limit. We evaluate engines in terms of power and efficiency, so I'll show those. I'll show that the calculations check out in some numerical simulations. I'll mention what advantages this engine has over a couple of competitors and talk about opportunities for future work. So our setup can consist of a chain of qubits, quantum two-level systems, such as might be realized by ultra-cold atoms. I'll label them from 1 to n. Now here I'm showing qubits or arrows pointing upward or downward as a cartoon. Earlier, I talked about ultra-cold atoms and showed that they could be present or absent. The two are equivalent pictures. They're interrelated by Jordan-Wigner transformation. So sometimes I might talk in terms of spins pointing upward or downward. Sometimes I might talk in terms of fermions that are present or absent. Such a system can be governed by a Hamiltonian like the following. It's a disordered Heisenberg model. It has two terms. One term is a nearest neighbor hopping and repulsion. The other term is the random garbage, this external disorder potential. We construct it in a numerical simulation as follows, and we can think of it as a field pointing along the z direction. So suppose that we want to construct the random disorder potential and how it acts on site J. We'll pick a number J, H sub J, a random number between -1 and 1. Then we'll multiply it by the overall disorder strength, little h. H is a parameter of our Hamiltonian that can change with the time t. This alpha sub t is some parameter that will tune between 0 and 1. And the value of the parameter alpha sets the strength of the overall strength of the disorder potential. Out front of the Hamiltonian, I'll have a couple of factors. This is the energy density or approximates average energy per site. It's the unit of energy. And this is a normalization factor that ensures that the average gap of the Hamiltonian remains constant throughout the cycle. That isn't really necessary. We just put it in there for bookkeeping reasons, because you could run a different sort of quantum engine in which you just expand and contract the entire bandwidth. That sort of engine wouldn't take advantage of the athermality of many-body localization. So when we calculated the work that we could get from our many-body localized engine, we just wanted to calculate the work that we could get from using properties of many-body localization. We didn't want to sneak in any of the work that you could extract using this bandwidth engine. So we made sure that the bandwidth of the Hamiltonian stayed constant throughout the cycle by dividing by this factor. So it's there to keep us honest. This disordered Heisenberg model has two regimes governed by the strength of this disorder potential, or really the parameter alpha sub t. I mentioned we can tune alpha between 0 and 1. When alpha equals 0, then the disorder potential is very small, in particular in comparison with hopping and interaction. In this regime, the system is either just weakly localized, or it's actually in a whole different phase of matter, a thermal phase, where entanglement in particles can spread out quickly. If alpha equals 1, then H is much greater than 1, the disorder strength is much greater than the hopping frequency, and the system is deep in the many-body localized regime. These two regimes have different energy level statistics.
I'm sorry.
Hello?
Can you go back one slide, please?
Sure.
Just to remind me again, you said when alpha equals 1, then H is much larger than 1. I probably missed the functional dependence of H of alpha.
We could make it linear.
But why is, I mean, so when alpha equals 1, H is much larger than 1, what does it mean? That there's a big prefactor, H is linear in alpha, but has a huge prefactor, or what is meant by that?
It could be. Large prefactor with a small offset.
Okay, so you didn't define it yet, so I didn't miss anything.
Yeah, it's the exact functional dependence doesn't matter at all.
Sure, but
the only behaviors that matter are
I was just worried that I missed
okay.
5 minutes earlier that you a point where you defined it, but okay, cool, thank you.
Okay, yeah, these are the only two behaviors that we need. And if anyone needs clarification during the talk, then do feel free to let me know. These two different regimes have different types of energy level statistics. Here's what I mean by that. We're not interested only in one particular Hamiltonian. We're actually interested in a whole class of Hamiltonians. Different members of this class correspond to different disorder realizations, different sets of little h sub j for where that set runs across the sites j in the lattice. So we could, in say a numerical simulation, create many disorder realizations by drawing random h sub j's many times. So we're actually interested in a whole class of disordered Heisenberg Hamiltonians. So suppose that we randomly pick one Hamiltonian from this class, and we know that it has some energies, and somewhere around the middle of the spectrum, there is some energy, let's call it E naught. Just above that is a gap. What is the probability that that gap is of size delta? That's called the gap distribution of this class of Hamiltonians. And the gap distribution can have very different functional forms depending on which regime we're in. For instance, suppose that alpha equals 0, so that the disorder potential is low, is small, and the system is in its thermal phase, or in a slightly different version of the engine, just the weakly localized regime. But for the moment, let's talk about this actual thermal phase of matter, which is distinct from the many-body-localized phase of matter. What do I mean by thermal phase? Technically, I mean that the Hamiltonian satisfies the eigenstate thermalization hypothesis. This is an equation that helps us understand how thermalization emerges in isolated quantum many-body systems whose Hamiltonians are chaotic. If our Hamiltonian satisfies the eigenstate thermalization hypothesis, then local observables will thermalize in the following sense. Suppose that we prepare our whole system in some pure state psi. We time evolve the system for a while. We time evolve the system for a long time. Then we take an expectation value of some local observable O. And actually there should be an integral here and a 1/t so that we take the long time average of the expectation value. That approximately equals the expectation value of the observable in the corresponding thermal state. So that's what I mean by thermal. Furthermore, the eigenstates of these Hamiltonians are very entangled, so that if you measure the system locally, you can't get any information that, because the system is so highly entangled, all you see is a thermal state. The gap distribution looks as follows, and for those who are familiar with gap distributions, I'm going to use the Gaussian orthogonal ensemble rather than the alternatives, just for basically convenience. The gap distribution can be calculated from random matrix theory, and it looks like this. So let me draw this out. Here's how the function looks. Along the x-axis, we have the possible sizes of the gap delta. Along the y-axis, we have the probability density associated with any given gap. This average delta here and here is the average gap of the Hamiltonian. Suppose that we are interested in small values of delta. So delta values over here. This exponential, because of this here, is going to be very close to 1. So we can basically ignore it. And this linear factor is going to dominate this function. So over here near the origin, the slope is approximately linear. On the other hand, if we look at large values of delta, those will pull this exponential downward towards 0. And so we see that this tail is pulled downward. And then there's this peak in between the two extreme behaviors. This region near the origin is particularly useful to look at. As the size of the gap approaches 0, the probability of a gap's being of that size approaches 0. In other words, energy levels don't like to be right next to each other. The gaps don't like to be 0. So we say that the energy levels repel each other. This is characteristic of the thermal phase. The opposite phase exhibits a contrasting behavior. Remember, when alpha equals 1, the system is in the deeply localized regime because the external disorder potential is very large. The gap distribution is called a Poisson distribution. It's not actually a Poisson function, but it's derived from one. So this function is just a simple exponential. It looks like this. Again, here are the possible sizes of the gap. Here's the probability density, and here's the average gap. We can again look at small values of the gap. As the gap approaches 0, the probability density does not approach 0. So the many-body-localized regime lacks level repulsion. This is a second way in which many-body localization is unlike a system at thermal equilibrium. So many-body localization, that phase of matter, is unlike the thermal phase of matter in terms of its gap distribution, because the gap distribution does not exhibit level repulsion. But we'll take advantage of this property in an Otto cycle that we'll construct for our engine. First, does anybody have any questions? Okay. The Otto cycle is
Sorry, Nicole.
Hello?
I have a question. It's a bit confusing that you speak about gap distribution. I mean, what you mean by that is a probability that the distance between two nearest eigenvalues is delta or not?
That's how I define the gap distribution, yes.
Yeah, but because this is known as spacing, nearest neighbor spacing distribution in random matrix theory, and the gap distribution would be the probability that the gap between two eigenvalues is larger than delta. So this is something different in random matrix theory.
Maybe the two communities that we come from have different definitions for the same word. Or the same term. It sounds like that might be the case.
Yeah, it seems, because I never heard it in this, even not in many body systems, but I don't know. Okay, so just a remark.
Okay. Any other questions? Okay. The Otto cycle is similar to the Carnot cycle, which is usually given more coverage in statistical physics classes. So it operates in most cars. It also has 4 strokes, similarly to the Carnot cycle. 2 of those strokes are isentropes, during which the entropy remains constant. 2 of those strokes are isocores, during which the volume remains constant, at least in the conventional version of the Otto cycle for an ideal gas. When we draw out an engine cycle, often we use a pressure volume diagram, but the pressure and the volume are not the variables that are most relevant to our quantum many-body system. So I'll use different axes. Along the x-axis, I'll plot the external disorder strength. Along the y-axis, I'll plot energies in the spectrum. Remember, when our parameter alpha equals 0, the system is in its thermal regime or weakly localized regime. When alpha equals 1, the disorder potential is strong. The system is in its deeply localized regime. I'll sketch representative energies.
Nicole, sorry, just to be sure. I mean, here you are not, or better, you are changing h via alpha. You're not changing the functional form of h of alpha, right?
Right.
Okay, good.
The energies in the thermal regime tend to be somewhat evenly spaced out. So the typical gap is not too far from the average gap. In the deeply localized regime, small gaps and large gaps appear more frequently. We start off our engine cycle with the system in its thermal regime in equilibrium with a temperature T sub H bath, a hot bath. So the density operator of our quantum many-body system is in this thermal state. We can use the statistical interpretation of the density operator to imagine that in each trial, the system begins on some particular energy level that is selected according to the Gibbs distribution. At the beginning of our cycle, the system is in this thermal state. We disconnect it from the hot bath. We, during stroke 1, which is an isentrope, tune the Hamiltonian from the thermal regime to the deeply localized regime. In an initial approximation, we assume that the tuning is very slow, quantum adiabatic, so that the system always remains on the same constant or on the same updated energy eigenstate. But after making that initial approximation, we add in diabatic corrections. During this tuning, the engine's energy is moving downward. The engine was disconnected from the bath, so the energy that comes out must not be heat. Instead, according to the first law of thermodynamics, it must be work. So our engine performs positive work during the stroke of the cycle. And here, during stroke 2, we hook up the system to a cold bath at a temperature T sub C. We demand that the cold bath have a bandwidth, WB, much less than the average gap. This ensures that the engine will drop down just across these small gaps that are more prevalent in the deeply localized regime. Meanwhile, the engine emits positive heat or absorbs negative heat. During stroke 3, we tune back from deeply localized to thermal. Again, the engine moves downward in energy space. So again, the engine performs positive work on average. During stroke 4, we re-thermalize the system. So we reset the engine to its initial states. And on average, the engine absorbs net positive heat. So
sorry, perhaps a super naive question. Why we are sure that doing this adiabatic deformation, the energy of the level always decrease?
That's basically what I was about to get to just now. So we saw that during the 2 tuning strokes, the engine performs net positive work. And why is that so? It's because we took advantage of MBL's gap statistics. We ensured that the engine over here would drop down just a small gap that is more prevalent in the MBL Hamiltonian spectrum than in the thermal Hamiltonian spectrum. So we selected out this small gap in the MBL regime to ensure that the engine would traverse this trapezoid with the narrow snout in the deeply localized regime. And that's why both these lines slope downward, because we took advantage of MBL's quote unquote athermal gap statistics.
Mm-hmm.
Can I add to, can I?
Sorry, please, go.
Yeah, I don't see still why on the right side, the 2 levels, why couldn't they be just shifted upwards or downwards, for example?
They could. So, and you can draw out all the possibilities. So this little gap could be in between these 2 levels. It can be above these 2 levels. It can be below these 2 levels. And if you work out the geometry, then you'll see that still on average, the net work output is positive. And since it was a number of years ago that I did this calculation, I don't remember if you actually have to take the average or if in basically every case, the net work output is positive, but at least on average, the net work output is positive.
Okay, thank you.
So essentially, yes. Okay, now I understand. I mean, it's possible that in one of the two you will increase, but in the other you will decrease more, and so at the end you tend to decrease.
Right.
Okay.
Exactly.
Got it. Okay. Okay.
But you might notice a problem. The number of sites in our engine we denoted by n, and the size of the energy band is proportional to n. On the other hand, the number of energy levels is proportional to 2 to the n. So the size of the average gap is proportional to n over 2 to the n. The size of the average gap decreases exponentially with the system size. Also, the average gap upper bounds the average work you will get out of one cycle, one trapezoid. So the average work outputted will approach 0 together with the average gap in the thermodynamic limit. So when our engine gets very, very large, it doesn't accomplish anything, which doesn't sound useful. But we can take advantage of the other way in which many-body localization is athermal. We can form a mesoscale sub-engine from about 10 sites, and our work output will be exponentially small in this number, this size of the sub-engine. Then we can put a whole bunch of sub-engines next to each other so that we have n total sites or sub-engines, they're related by a constant, together. The power grows linearly in the number of sites or the number of sub-engines. So it doesn't decrease exponentially in the number of sub-engines. You can furthermore put these sub-engines relatively close together because what happens in a sub-engine stays in a sub-engine because of the localization of many-body localization. Even if you put the sub-engines fairly close together, you don't have to worry that particles and information from one engine will spill very much into the next sub-engine. So the engine scales relatively robustly due to the localization that is inherent in MBL. We assess an engine, as I mentioned, by calculating the power and the efficiency. Let's start with the average work extracted per cycle. For background, we should discuss what work and heat are in quantum thermodynamics. In classical thermodynamics, we have a system of interest. It tends to be hooked up to a heat bath and a battery. So a system that can store fairly reliably the capacity to perform work. This could be a physical battery. It could be a rock that is at some height on a hill. It could be a wheel that is turning or not turning. We say that the energy that is exchanged with the heat bath is called heat, and the energy that is exchanged with the battery is called work. In quantum thermodynamics, we have a bit of a problem. We need to be able to measure heat and work, but the system might not even be in a state in which it has a well-defined energy. And furthermore, how do you measure the energy without changing the energy? So it's different. It can be difficult to come up with consistent definitions, operational definitions of heat and work in quantum thermodynamics. Different scenarios call for different definitions. So here's the one that we use that's very prevalent for slow processes. Let's call the internal energy of a quantum thermodynamic system the trace of the state with a Hamiltonian. We can use the product rule to calculate the two sources of change in the internal energy. First, the state can change. Second, the Hamiltonian can change. This state is the generalization for quantum systems of the phase-based density in classical statistical mechanics. As a classical statistical mechanical system heats up or exchanges heat with a heat bath, its phase-based density approaches the thermal phase-based density, which is the phase-based density of maximum entropy that is consistent with the constraints on the system. And entropy encodes uncertainty and disorder. Also, heat is energy that is, in a sense, uncertain because it's random, it's uncoordinated. So we call this term the heat that flows into the system. This change in the Hamiltonian comes from a change in some knob that we're turning. So it's a change that we have control over. It's controlled by some classical external parameter. Similarly, work is controlled energy. It can be directly harnessed to perform useful tasks, or it's well ordered. So we associate this term with the work that flows into a system. So we'll use these definitions with our engine. I'll make a few assumptions. First, I'll set Boltzmann's constant to 1. I'll assume that the cold bath has a small bandwidth. As I said, it should be smaller than the average gap of the engine. I'll assume that the cold bath is cold, the hot bath is hot, and these will define a parameter regime that you can actually meet. You can meet these constraints. But let's calculate the average work performed per cycle. According to the first law of thermodynamics, the total work performed by our engine equals the sum of the two heat quantities absorbed by our engine during the cycle. So here are those two heat quantities. This is Q4, this is Q2. This Q4 is approximately the average gap times the probability that the engine traverses this trapezoid completely in the correct direction. So really, this is the key step which determines whether the engine traverses the cycle. So a positive contribution to this heat quantity comes from the probability that the engine does drop down during the cold thermalization. But there's a correction because the engine might accidentally go upward across a gap instead of downward. Let's calculate each of those probabilities. What's the probability of dropping downward as desired during cold thermalization? It's approximately equal to this integral. So we're going to integrate over the possible values of this gap from 0 to the cold bath bandwidth, because that's all the heat that the cold bath can absorb, times the probability density associated with this bath, with this gap's actually being of size delta prime, times the probability that if the gap is of this size, then the engine drops downward. This exponential is approximately 1 because this gap to be dropped downward across is very small compared to the average gap by our assumptions about how small the cold bath bandwidth is. So we perform our integral and we get this result. It's normalized by 1 over the average gap. The primary contribution is the cold bath bandwidth, and then there's a finite correction because the cold bath might not be completely cold, it might not be at 0 temperature, so it could actually maybe excite the engine. Let's focus on that other possibility of exciting the engine. We have almost the same integral with almost the same factors, but there is an exponential decrease because it's more difficult for the engine to absorb heat. And we integrate this to find that the probability of rising depends crucially on the cold bath's temperature, as you would expect. And again, there's a normalization factor of the average gap.
Sorry, Nicole, I need a little bit of a supplement. I mean, I understand the fact that you integrate and let's say the first factor, which is the probability to have a certain gap. I don't understand the second term. Can you repeat?
This I tend to associate with detailed balance.
I see. Okay, go ahead.
And yeah, so similarly, if the cold bath has a positive temperature, which we assume that it does, then if you look at the thermal state will have most of its probability weight in the bottom level. And so when we're talking about the possibility of this process, this is the bottom level. And so the engine has a small probability of being at the top level after thermalizing.
I see. Okay. Okay, got it.
Okay. So we can put those probabilities together in Q4, the average heat absorbed during reset. We said it's about equal to the average gap times this difference of probabilities. So let's plug in. And we find that the dominant term is the cold bath bandwidth. And there's this finite temperature correction because the cold bath in reality is not going to be as cold as an ideal cold bath can be. But this finite temperature correction is much less than the dominant term according to our assumptions. We calculated Q4. Now let's calculate Q2, the average heat absorbed by the engine during cold thermalization. We'll perform a very similar integral. There's a negative sign here because typically and on average, the heat absorbed is negative. That is, the engine expels positive heat. And we have the same factor here and the same factor here, except we have now a delta prime that we're integrating over, because now we're not calculating just a probability, we're calculating an average heat quantity, an average energy quantity. We can perform this integral, and we get this expression, which we can break up to see its physical significance. This factor here, the cold bath bandwidth over the average gap, is very small by our assumptions. So the magnitude of this heat exchange during stroke 2 is much less than the cold bath bandwidth, which about equals the average heat that was absorbed during the reset step. Let's put everything together to estimate the average work performed per trial by one of our mesoscale sub-engines. This equation, we said, comes from the first law of thermodynamics. We can substitute in, this was our Q4, this is our Q2. And these two terms are small corrections according to our assumptions. We can calculate a lot more corrections because the hot bath might not be infinitely hot and the tuning might not be actually quantum adiabatic, but also those corrections are small. And according to our numerical simulations, the net work output is positive on average. So that's the total work performed per trial by a mesoscale sub-engine on average. The total work performed by our whole engine on average is that quantity above times the number of mesoscale engines. So how much is that? I just showed some analytical expressions. It'd be nice to get a sense of some numbers. So we did some rough order of magnitude estimates for a system of silicon doped with phosphorus. Now, this system actually had not, by the time of our writing our paper, been used to realize many-body localization. It had been used to realize Anderson localization. So you actually can run our cycle on an Anderson localized system, although it's a little less convenient there. So we estimated that the power is roughly 10 to the negative 16th watts. And what does that mean? We can compare with the power of another small motor, a motor that powers the flagellum of a bacterium. We estimated, or according to our rough estimates, the MBL-mobile's power is about 10 times greater. You can also estimate the power density, the power per unit volume. We estimated that to be 100 kilowatts per meter cubed. What does that mean? It's about 1/10 the power density of the engine in your car. So we probably will not have MBL-mobiles in our garages anytime soon, but the MBL-mobile isn't doing too badly. Also, to evaluate an engine, we calculate its efficiency, which is the net work outputted divided by heat absorbed during the stroke, in which, on average, the engine absorbs net positive heat. In our cycle, this heat quantity is Q4. And we said that the total energy, the total work output, it decomposes like this according to the first law of thermodynamics. So we can simplify the fraction and substitute in from the calculations we just did on earlier slides. Then we can approximate. So this is the efficiency of our engine. The cold bath bandwidth is much smaller than the average gap by assumption. So this factor really is small. We can compare with the efficiency of the conventional ideal gas Otto engine. when we run an ideal gas Otto engine, we have some ideal gas that we compress and expand between volumes V1 and V2. The specific heats of pressure, constant pressure and constant volume are here in this exponent. These two efficiencies can equal each other in the following sense. Suppose that I am a conventional thermodynamic agent who has an ideal gas Otto engine. It has some specific heats, and I compress and expand it between two volumes that I choose. And ideally, I can achieve this efficiency. And suppose that Dario is a quantum thermodynamic agent. I can hand my numbers over to him. He can choose a cold bath bandwidth and an average gap, such that his MBL-mobile Otto engine achieves the same efficiency. Both of these efficiencies obey the Carnot bound, the greatest efficiency of any engine that just runs between two baths of two different temperatures. That's 1 minus this ratio of those two temperatures. And this is comforting because I always expect that if you break the Carnot bound, then you are doing something wrong. I showed you some analytics and some estimates. We can check them in numerical simulations. Christopher did the numerical simulations. He was simulating a mesoscale sub-engine due to the power of his poor classical computer. He simulated a one-dimensional chain of 12 qubits subject to the disordered Heisenberg model that we saw earlier. And he performed the evolution using exact diagonalization. I'll show you results from the simulation of the adiabatic approximation. Christopher also did finite time simulations, but I want to show you this simpler version so that we don't get distracted by too many phenomena. Also, I'll show you the very simple case in which the baths have extreme temperatures, but you can check out our paper if you would like to see the cases in which the temperatures were finite. Let's start with the average work outputted per cycle. This is our analytical prediction. The average work outputted about equals the cold bath bandwidth. And that's what we see in our simulations. Along the x-axis, we have the cold bath bandwidth normalized by the average gap. Along the y-axis, we have the average work in units of the average gap. The red dots come from the simulations. Each was formed from 1,000 disorder realizations. And the error bars are too small for us to see. The blue line represents...
This is for 12 qubits, right?
Right.
Okay. Are the two agreements becoming better by increasing? How do they scale with the system size?
How does what scale with the system size?
Yes.
How does what scale with the system size? I didn't hear.
Sorry, the agreement between the theoretical and the, let's say, the numerical prediction, do they...
Well, here at 12 qubits, so my understanding is that 8 qubits is the minimal system more or less needed in order to see energy level statistics that differ significantly between the two phases. Christopher was operating at 12 qubits, and there was very good agreement. So this blue line represents the theoretical prediction, and especially since this gray area represents the only region that actually satisfies our assumptions, there turned out to be excellent agreement even outside.
Okay.
And we would have loved to have gone beyond 12 sites, but we just didn't have the computational power. It took quite a lot to get to this because of the sort of study that we were doing. You can also check out the efficiency. This was our prediction, 1 minus this ratio. So here along the x-axis, we have the ratio of the cold bath bandwidth to the average gap. Along the y-axis, we have the efficiency. Again, there's quite good agreements, particularly in the regime in which there's supposed to be agreement.
Do you understand the deviations out? I mean, you say the gray Y is the gray part is the part that, let's say,
where there's supposed to be agreements.
Right. And do you understand why? Because it looks that there is
we have
really,
some.
Yeah.
We have a number of expectations cataloged in the paper, I think. But when on the plots that show finite temperatures for the baths, then there are, no, actually, this can also happen at extreme temperatures, if I recall correctly. So I showed a toy model in which there's one gap on the left-hand side and one gap on the right-hand side that play important roles in the cycle. But there are corrections. For instance, you could have on the right-hand side a chain of 2 or more gaps such that the whole set of them is still smaller than the gap on the other side of the cycle. And so you should actually take into account that chain of small gaps in your calculations, but we can calculate, or we have a choice as to how high in order we take into account. And I think we took into account maybe 2 small gaps. But you can keep adding corrections like that.
Okay.
We can compare the MBL-mobile to various competitors. There's a whole list of competitors and comparisons to them in the paper in case you're interested. But there are a few worth mentioning. We saw that the MBL-mobile can scale robustly toward the thermodynamic limits because of the athermal property of localization. And this is in comparison with an engine that is similar, but just stays in the more thermal regime. Relatedly, the engine can achieve a relatively high power density because, and you can pack sub-engines relatively close together without their interfering with each other too much, again, because of localization. Also, suppose that you run an engine many times. The amount of work that the engine will perform will fluctuate from trial to trial. The MBL-mobile is relatively reliable because of the other athermal property of many-body localization. That is, it has gap statistics that are very unlike the gap statistics of the thermal phase. And this reliability is relative to an engine that would be somewhat similar, but instead of ratcheting the engine between the strongly localized regime and the thermal regime, you just keep it in the strongly localized regime and ratchet within a cycle instead of between the two regimes, just from disorder realization to disorder realization of the same strength. So it's really worthwhile to take advantage in one cycle of the difference between localization and thermality. If you perform enough trials with an engine, eventually in some trial, the engine will perform net negative work, or it will absorb net positive work. I call these trials worst case trials. There are relatively few worst case trials undergone by the MBL-mobile, again, because of athermal gap statistics. This work opens up a number of opportunities. First, many-body localization has been realized experimentally. And so one could realize the MBL-mobile experimentally. I'm working with a team that is trying to do that with superconducting qubits. We'll see how it works out. But a number of platforms are viable. Our cycle we showed works. We did not show that is optimal. In fact, it's not optimal. You could try to optimize it using various tricks. For instance, shortcuts to adiabaticity, which let you change a Hamiltonian quite quickly while achieving results similar to the results that you would achieve if you tuned quantum adiabatically. This also opened up the age of thermodynamic applications of many-body localization. Many-body localization had been known to be potentially useful in memories for quantum computers, but just as information processing or memory storage is an information processing task, there are thermodynamic tasks. Work extraction is just one of them. So you could imagine running the cycle backward and refrigerating You could sort of dream of a quantum many-body refrigerator that cools quantum many-body systems so that they operate in the quantum regime. Also, you could imagine ratchets or diodes formed from many-body localization. In fact, I think someone might have proposed either a ratchet or a diode sometime after our paper came out. Also, this shows that you can regard athermal level statistics as a thermodynamic resource. Usually thermodynamicists think of probability distributions over phase space or density operators as things that can be athermal and so resources in thermodynamic tasks. But here you can also regard athermal level statistics as a resource. You might be able to use them in other thermodynamic tasks, or there could be other objects that we haven't even thought to regard as athermal potential resources. So if you're interested in seeing or hearing about the MBL-mobile with much better pictures, then I can point toward this book that's coming out soon. The images are by Todd Cahill, who is a much, much better artist than I am. So he drew these beautiful pictures. This is his illustration of the MBL-mobile, which is covered in, if I recall correctly, chapter 7. So that has more detail about the story behind the MBL-mobile. But in summary, we saw that if you have random garbage, namely a random disorder potential, together with interactions, you can achieve an interesting phase of matter, quantum many-body localization, that's in two senses athermal, or not as at thermal equilibrium. We saw that those two types of athermality can be attributed to localization, the particles don't spread out much quickly, and gap statistics. We constructed a 4-stroke Otto cycle. We calculated the power and efficiency. We saw how that panned out in numerical simulations. We saw some advantages of the MBL-mobile and saw that much is left to be done. So, thanks for your time.
Thank you, Nicole, for this excellent seminar. Let us thank Nicole. And we are open for questions. Tawfiq?
Yes, thank you, Nicole, for such a great talk. I have some questions, and I'm a student, so some of the question might be very basic. So first, in order to realize this this cycle using many-body localization, then we have to have, let's say, a perfect control over disorder strength. So I'm just curious whether this is feasible experimentally, and if yes, how?
We do need to tune the disorder strength upward and downward across the cycle. And I don't know if we need perfect control, since that's something that we can never achieve. Certainly you would need control. If there is a lack of control, then we could, so let's say some imperfection in how the disorder strength would change, then we should be able to calculate corrections to the average work outputs that are attributable to this imperfection, similarly to how we calculated corrections to the average work outputs due to diabatic jumps in the tuning, due to the tuning, and due to finite temperature baths.
Mm-hmm. So can you give some, let's say, some intuitive picture of how can I tune disorder strength in experiment?
One can increase the pressure on the particles and decrease. So that actually changes the strength of the other term in the Hamiltonian, the hopping potential. So it changes the frequency with which the particles hop, which is equivalent to changing the other term.
I see. So you tune the hopping parameter instead of the disorder, so the relative strength would change.
Well, you can also, let's say, increase the magnetic field. I mean, these are fluctuations around the magnetic field. So if you increase the strength of the magnetic field,
exactly.
Yeah.
But you have to keep bandwidth constant, right? The total bandwidth. So this is
that's
maybe
just for bookkeeping purposes. So we, in our calculations, kept the bandwidth constant so that we could separate the work that comes from the athermality of many-body localization from the work that comes from a bandwidth engine action. But if all you want to do is extract some work, then you don't have to be as careful about getting rid of the bandwidth engine effects.
Mm-hmm.
I have another question. So you said that the engine has a good reliability. So in your paper, do you quantify the reliability of the engine? Okay, thank you.
Yeah, that calculation is either near the end of the main text or in the last appendix.
Okay. Last thing. So I usually read papers about like small engine. So when it comes to, let's say, storing works, it's sort of intuitive in a sense. I can just connect it to a qubit or something like this. But in a many-body system, I'm curious of how to extract work. Like what kind of mechanism can be used?
Yeah, we were using an implicit battery model. So we didn't specify how the battery would look, because that would require us to specify a platform, and our calculations were more general than that, so that they could accommodate basically whatever platforms MBL is realized in. But suppose that you had ultra cold atoms for your MBL-mobile, then you could potentially stick them in a cavity, and the cavity modes could potentially store the work that comes out.
I see. Okay, thank you.
Okay, we have more questions from Alexei.
Yeah, thanks. I have two questions. Basically, one is how would these results depend on the type of the many-body localized phase that you have?
The type of the many-body localized phase?
Yeah, you consider the random Heisenberg chain. I could think of, for example, taking, say, this Otto-free many-body localized system with perhaps also spins, or quasi-periodic system, or would there be any significant
when you say quasi-periodic system, do you mean a driven system?
Well, that was, let's say, my second question. No, I mean, literally your randomness is quasi-periodic.
Okay.
So do you think there will be any qualitative difference?
As long as you have gap statistics and localization, then this should work.
Okay. Yeah, and then the second question is, what happens if, again, would there be any difference if you consider perhaps either instead of the thermal or localized phase, a bed metal? Or
sorry, I didn't quite hear that. Could you repeat it?
I mean, if you replace, so I mean, in your Otto cycle, you basically go from thermal phase to localized phase, if I get it correctly. So I'm asking, would there be any difference, like, or a drop in efficiency if you replace one of those phases with bed metal phase or a multifractal phase? So like the one you probably get in between thermal and localized phase.
So the engine benefits from having one part of it be in a phase that has Poisson gap statistics, and the other part of the cycle be in a phase associated with Gaussian type gap statistics. And so if you have, instead of one of those two, something in between, then that would decrease the engine's effectiveness, for instance, in terms of the reliability and few worst case work cycles. Also, the average work outputs, I would have to think about whether the average work outputted would change. My first guess is no, but I would have to think about it some more.
Okay, yeah, I'm sorry. The final question is, would it make sense to try and implement a similar cycle in a system with a mobility edge?
What do you have in mind? As in, what advantage might it give?
Now I'm just thinking that in a system with a mobility edge, you basically have, I mean, you can probably, by pumping energy in the system, you can put it either in localized or thermal phase.
All right, sometime after our paper came out, John Gould's group wrote a paper about mobility edges. I know that they had in mind an engine. Maybe they put the idea in that paper, or maybe they put it in a later paper, but I think this is something that they've thought about.
Okay, thanks.
I do apologize. I'm supposed to head out now.
Okay, maybe a short question now.
Sure.
Oh.
Yeah, can I ask a short question? Or you wanted to ask till and I forgot?
No, go ahead. Go.
Okay, so can you, I mean, I'm a little bit confused by the idea of the sub-engines, let's say, can you go back? Okay, you removed the screen share, so okay, I can ask. I mean, you say that one of the main features is that when you do this, let's say, some sub-engines that are, let's say, put close to each other, you say one of the main thing is that essentially they don't communicate, because in MBL they don't communicate. But when you go to the thermal phase, yeah, but when you go to the thermal phase, this property will be lost. So is that
agreed? So that's why in some cases I said that we tune between deeply localized and the thermal phase, or we tune between deeply localized and shallowly localized. So if you had just one mesoscale subengine, you could tune between deeply localized and thermal. But if you want to chain a lot of mesoscale subengines together, then it's useful to tune between deeply localized and shallowly localized, so that you can always take advantage of some localization.
I see. Okay. And the other question is the following. I mean, if you want to make effective your machine, your idea, it's crucial that the bandwidth of the cold bath is always, let's say, much smaller than the mean level spacing, let's say, than the gap, as you call it. Now, the point is that the mean level spacing or the gap in the thermodynamic limit go to 0. So how feasible is to keep, I mean, I'm wondering how feasible, yeah.
That's why we use those mesoscale subengines. So each one couples to a bath locally and doesn't couple to an infinitely long time. So the cold bath can only access a small region, which is associated effectively with a larger gap.
I see. Okay, got it. Okay, thanks.
Yeah, thanks for the questions.
Okay, with this, we conclude our today's seminar. Let us thank Nicole again.
Thank you for hosting me. And sorry about having to leave soon, just because of the time difference.